Okay, let's get started. So this week we're talking about entanglement, but before that, I want to give the answer to the question I posed last week. So let's go full screen. So the question was, if there are two communicating parties, Alice and Bob, who are doing the BB84 protocol, and there is an eavesdropper, Eve, in the middle, who will intercept all of Alice's qubits. And what she'll do is that she'll measure Alice's state, and then she'll forward her measurement outcome to Bob. So the question is, what is the error rate that she'll introduce in Alice and Bob's final key? So this is a protocol. So Alice would decide on a bit string to send to Bob. So this is the first line there, given by a string of zeros and ones. And Alice will choose the encoding bases. So these are the X and Zs. And Bob would choose to randomly measure in either X or Z. So now Eve, who is in the middle, because she doesn't know whether Alice would have prepared in X or Z, therefore, the best that she can do is also to choose to measure in either X or Z. So, as we were talking about last time, it doesn't matter. So half the time, Alice and Bob will have chosen different bases. So this is given by the ones in black here. So for example, in bit B, Alice has chosen X and Bob has chosen Z. So these ones don't matter because they get discarded anyway. And now the ones which do matter are the ones where Alice and Bob have chosen the same basis. So this is given by, for example, column A here, column C, column D, E, and etc. So these are highlighted in blue. Now, half the time, Eve would have chosen the same basis as Alice and Bob. So for example, the one that are labeled in C there, they've all chosen to measure in Z, or prepare. Alice has chosen to prepare in Z, and both Bob and Eve have chosen to measure in Z. So in this case, Alice has sent a ket1, in which case Eve would measure a ket1 and forward it onto Bob a ket1. So here, all of Alice, Eve, and Bob's states are the same. Well, the cases where Eve would potentially introduce an error are the ones where Alice and Bob has chosen to measure the same basis, but Eve has chosen a different basis. So in the first column labeled A there, say for example, Alice is prepared in in X and Bob has measured in X, whereas Eve has measured in Z. So the formal question is, what is the probability that Bob's bit, given in a question mark there, will be different from Alice's bit? So the answer is, so here, the probability that Eve would have chosen the same basis is a half. So half the time, she'll just get it right. And the other half of the time, she would have chosen the wrong basis. However, when she does choose the wrong basis, say, for example, Alice here would have prepared a plus state, and Bob would have measured in X, but Eve has measured in Z, right? Which means half the time she'll get a 0, and half the time she'll get a 1. However, when she forwards this onto Bob, then once again, when Bob measures X on the 0 or the 1 state, half the time Bob will either get a plus, and the other half of the time he'll get a minus. So if Bob happens to measure a plus, then this will coincide with Alice's classical bit. So Bob would have attributed a plus to a 0, so that's the same as Alice's 0. But the other half of the time, Bob would have measured a minus, which means he would have measured a 1. So the final answer is a quarter, because half the time half the time Eve would get it right. The other half of the time Eve would get it wrong, but when she gets it wrong, with half the probability, the bit will the bit will collapse to Alice's preparation anyway. So if you're doing BB84 with somebody and you're measuring, so for example, so you have your final key, right, that you have sifted or you've post-processed, and you saw that you have a quarter of the bits which are wrong, then this means, or most likely means, that somebody is just in the middle taking everything Alice is sending to you and forwarding you the measurement result. Okay. Okay, so this is everything that was just talked about. I'll leave that in the slides. Okay, so one comment that I wanted to make was, so here, obviously, Eve introduced quite a significant error in the final keys between Alice and Bob. And of course, this, if we see that there is an error, they will just terminate the protocol and not use that key for anything they want to communicate securely. So an attack on a quantum key distribution system or any more specifically, quantum key distribution system is considered successful if the eavesdropper is able to obtain a significant amount of the keys shared between Alice and Bob without getting caught. So how can she do that? She might use a slightly more subtle technique than the send and intercept attack, but yeah, this is slightly beyond the scope of this course. Okay, let's talk about entanglement. So, or let's first talk about composite systems. So we mentioned a bit about this earlier on. So because we can't really talk about entanglement without talking about more than one qubits. So if we have two independent quantum systems, A and B, and we'll talk about two qubits here, or two qubits possessed by Alice and Bob respectively, we typically write the composite state as a tensor product given by this notation here. So we can label these as lambda A and phi B. The subscript just denotes that Alice has it, and the B denotes that Bob has it. So lambda A could, for example, be an arbitrary superposition of alpha 0 plus beta 1, and phi B can be an arbitrary state with the coefficients delta 0 and gamma 1. So just a reminder that alpha, beta, delta, and gamma can be arbitrary complex numbers. So we know that superpositions are allowed, so we're allowed to sum over the coefficients. And however, we can note that maybe not all states can be written as a tensor product. So for example, the state in equation 5 there is one such a state. So there should be a bracket here. So if we have a 0, 0 plus a 1, 1, then you can try all you want, but the state in equation 5 cannot be written in the form of equation 4. And equation 5, equation 5 there is actually what we call a maximally mixed state. Sorry, maximally entangled state. So here are some properties of a maximally entangled state. So if we write, we can write the state in this form. This means, okay, sorry, there's actually a typo there. There should be 0A, 0B plus 1A, 1B, which denotes that one qubit is possessed by Alice and the other one is possessed by Bob. I'll correct this notation later. Oops. So if the two parties do possess such a state, it means that, one, any action of Alice on her system is going to change Bob's. So let me just quickly. And any measurement that Alice might perform will review information about the state of her qubit as well as Bob's. So for example, if here Alice chooses to measure in the computational basis or the computational basis, which is Z, or the X basis, which is the plus or minus, she will collapse her part of the state onto one of those states, and she'll immediately know what Bob's system would have collapsed to. This is true regardless of the distance between Alice and Bob. So this is actually quite surprising because we talk about the inability to perform faster than light communication, but the collapse, so when Alice measures her system, this will immediately collapse Bob's. And collapse of the wave function is, as tested by experiments, as far as errors go, is instantaneous as far as we can tell. A follow-on point from that is that 3, so the collapse of the wave function being instantaneous does not imply supernuminal communication. So I want to show you some evidence for number 3 there. So if you do a quick search on the literature, people have done all different sorts of experiments. This is quite a recent paper. They say that, so they did this experiment using photons. So they say in the final sentence of abstract, we find no additional delay within our accuracy and set a lower limit for the speed of the collapse of the quantum state to 1,550 times that of the speed of light. So this is one group of people. Another group of people who managed to close the Bell's inequality, which you might have heard of, which talks about locality and hidden variable theory, which stuff that Einstein hated. So what they did was they managed to entangle 2 particles about 1 kilometer apart, and they were able to violate Bell's inequality. So if you haven't heard of it, I might not go into details, but that has to do with the fact that so Einstein didn't like the idea of this non-local wave function. So, Alice does something and then something immediately happens to Bob. So he proposed where, so maybe, we don't know what the wave function is going to collapse to, but perhaps there is some hidden variable that we have no access to. So maybe the state is already in the 0 or it's already in 1, but you just don't know. So Bell's inequality disproves that. So this experiment was done in 2015, and there is a satellite again which managed to distribute an entangled state between 2 distant ground stations separated by 1,200 kilometers apart, and lo and behold, quantum mechanics holds. So we're very happy about the wave function collapsing instantaneously. So, but if you're not convinced, we can talk about it later. I want to quickly correct this notation because that might become confusing. The correct labels on this version over here. Okay. Okay, good. Okay, so that should have changed. So, as I was saying before, these two qubits, one of them belongs to Alice and the other one belongs to Bob. This one state here belongs to Alice and this state here belongs to Bob. Okay. So entanglement can be, well, okay, it dictates correlation between the states possessed by two parties. So it means, so here we're saying that if Alice measures her state to be 0, then she immediately knows that Bob has a 0. But what is the difference between, so we call this, we say that Alice and Bob's measurement outcomes, the measurement results of Alice and Bob's are correlated. So, however, but what is the difference between the two parties possessing this maximally entangled state versus something that we can describe classically? So let's say that this source in the middle here spews out entangled photons in either direction, or half the time the source will send out two zeros, so it sends Alice a 0 and Bob a 0, or the other half of the time it sends Alice a 1 and Bob a 1. So in that case, their measurement outcome in the 0 and 1 basis are still perfectly correlated, because here, you know, Alice gets a 0 and Bob gets a 0, so they will measure a 0, 0, and Bob will get a 1, and Alice will get a 1. Okay, so the difference is this. So I want to do this on the board. So here we're saying that, okay, Alice and Bob are both measuring in the computational basis, which is fine. But what if we tilt the basis of measurement, and we measure in X? Now, so let's do this on the board. So what I claimed before was that if Alice measures in the plus basis, Bob would also measure in the plus basis. So I want to do 9 and 10 on the board. Stop presenting. And present now. Window. Okay, so I hope that this is a whiteboard that is on. Oops, sorry, okay, I think I'm back. And I want to present to window. Okay, good. Okay. So the state that is shared by Alice and Bob is this thing. Okay, so I claim that the probability that Alice will measure a plus is 1. I don't want to go into the full maths, but I can show you that if Alice has measured a plus, so okay, you get a factor of 2 here. So if Alice is doing measurement on her part of the state, it means that she just tags along a so mathematically it means you tag along an identity operation on Bob's since he's doing nothing yet. But let's omit that for clarity. So this will give you 0, measure on 0, tag along with the 0 because that part belongs to Bob and that's not changed. And these belong to Alice. plus, okay, so you see what I mean. So this is Alice's system, and this is Bob's system. And you end up with a 1 plus 0, 0, plus a 1 with 1, 1, plus a 1, wait, sorry, there should be a 0. Wait, no. 0 with a 0, 0, 0, sorry. So you have a 0 with a 1, 1, and then you have a 1 with a 0, 0, and then you have a 1 with a 1, 1. Of course, then this goes away because this becomes a 0. This goes away because becomes a 0. So what we end up with is the 0 on Bob's side plus a 1 on Bob's side. So with the normalization of 1 on square root 2. So this is saying that if Alice projects her state onto the plus state, then it immediately should also collapse Bob's state onto the plus. So now, when Bob measures in X again, he'll get this with probability 1. And same goes for the minus. So now, let's start again with 0, 0 plus 1, 1. So if Alice measures a minus, so you have 0 going with 0, 0 minus, oops, minus, wait, this is a plus 0 with a 1, 1, minus 1 with a 0, 0, minus 1 with a 1, 1. Okay, so, with some normalization, this is proportional to 1 over square root 2. 0 minus 1 on Bob's side. So what this is telling you is that if Alice measures a plus, Bob will also get a plus. And if Alice measures a minus, Bob would also measure a minus. So I think we're happy with that for the time being. Now, however, if half the time Alice, so this is what happens if the state is actually truly entangled. But now, say for example, if the state that is spewed out by the source is this, is simple to 0, 0 half the time, then now I want to make Alice and Bob measure in the plus and minus spaces. Okay, so the 0, 0 state, Alice, Bob, I can write this as this thing. You can, okay, without the square root 2. Plus, 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 minus, plus, minus, plus, plus, minus, minus. If you want to check this, you can simply write 0 as, for example, plus minus, minus, right? A half. Oops. You can check that this is true. So when you substitute this into the tensor product, you end up with this whole superposition over here. And same goes with the 1, 1. You can check that this is equal to a half, plus, 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 wait, a minus, plus, minus, oops, minus, minus, plus, plus, minus, minus. Okay. Now I want to go back to the slide. A window. Okay, so that's equation 13 over there. So now, so there is perfect correlation if Alice and Bob measures in the 0 and 1 bases. However, if they now measure in the plus and minus bases, you can see that all the probabilities are equally likely. So all the different outcomes, so because there are only 4 different possibilities, right? So Alice gets a plus, Bob gets a plus, Alice gets a plus, Bob gets a minus, and so on and so forth. Now, all of these outcomes are equally likely, which means the measurement outcomes are completely not correlated. So this is different from when you have a entangled state, where you have perfect correlation in both the Z basis and the X basis. So in some sense, if you possess half of an entangled state, this gives you a lot of information about the state of the other party, and it's a somewhat unnatural amount of information about the other half. So this is one of the things which are weird about it. So, so in summary, you have correlation in multiple bases, and the collapse of the wave function is instantaneous. So these are the weird things which you might not have seen before. Okay. Okay, actually, that was what I was hoping to talk about. However, we have a bit of time, so I want to talk about another quantum key distribution protocol based on entanglement. So let's go back to the board. Stop presenting. Set now a window. Share. Okay. So this is the we call the E91 protocol for QKD, because this is based by Eckert et al. So it was derived in 1991, hence the protocol E91. So it is very similar to the BB84 protocol. So remember that in the BB84 protocol, Alice is generating a classical bit, and she's choosing a basis Z, and then she's sending Alice, and then she's sending these to Bob, who's choosing to measure in the X and the Z. So let's say this is BB84. So in the E91 protocol, basically, so you have Alice and you have Bob. So there is a source in the middle which is spewing out entangled states. Oops. Of this form. 0, Alice, 0, Bob, plus 1, Alice, 1, Bob. So here, basically, Alice just chooses to measure in the X or in the Z. And then Bob will randomly choose to, once again, measure in the X or the Z. And now, since we saw that entanglement implies perfect correlation in both of these spaces, now Alice and Bob cross-check in each stage. So for each of the states that they measured, whether they measured in the correct basis. So whenever they did, they will keep that measurement. And whenever they didn't, they will discard that measurement. And basically, it follows straight from BB84 that if they measured in the correct basis, then the measurements should perfectly correlate and vice versa. So you might have noticed, you might ask, so what's the difference between these two protocols? So the difference is that here, Alice is randomly generating the classical bit at the beginning. So here, that randomness generation is replaced by the randomness in the measurement. So in the sense that here, if Alice is measuring in the 0, she doesn't know in advance whether the state will collapse to a 0. And it's because these two would occur with equal probability. And this also brings us to the point I was talking about before, where this strictly does not imply that you can do faster than light communication. Because it's because that you don't know what the state is going to do, right? So communication implies that you can send information from one side to the other. So let's start again with a new page. So if I start off with, I'll use black. So if I want to start off with this state, well, this is equivalent to now, Alice can measure the state all she wants, but she does not control over but she does not control onto which state that is going to collapse. So, she can measure in the 0, 1 basis, but whether her state collapses onto the 0 or the 1 is out of her hands. Same goes for the plus state. So they can choose to measure in the plus or minus basis. Oops. They do not know in advance whether the state they'll end up in is the plus or the minus. So probably a very bad analogy is that they could be, so Alice and Bob could be sitting on 2 different planets, and there's someone in the middle who is waving a torch at them. So we know that the torch is going to go, if I send Alice 2 light signals, I'm also going to send Bob 2 light signals. And on the other hand, if the torch sends Bob 1 light signal, it's also going to send Alice 1 light signal. So the 2 communicating parties know how many signals the other person is going to get immediately. However, they have no control over what the person with the torch is going to do on the other planet. Okay, so I think so. That was the content that I was going to talk about today. Are there any questions?
No, not really.
Okay. So next week, if so, I think next week we are going to talk about the superdense coding protocol as well, and maybe teleportation if I get to it. But most likely I think we will. Yeah, I think so. Okay, cool. So, if there are questions, or if you have any questions in the meantime, feel free to email them to me. Otherwise, I'm happy to take them next time at Thursday at 5 o'clock.
Yeah. Okay. Thanks.
Cool. Cheers.
Thank you.